Yeah, hey everybody. Super cool to be talking in front of you now. And let me just share my screen. So Suraj and I, we're going to talk a bit about how to use JAX and Flax in transformers. I think yesterday you've seen how to, or you've heard how to use JAX and Flax in general. So today it's a bit more about how we integrated JAX and Flax into transformers. So Suraj is going to kick it off by the design philosophy for JAX and Flax in transformers, and also explain a bit more how the models are kind of built up, how the inference works, and how the training works in transformers. Then in the second part, I show you how the Hugging Face Hub can be used for collaboration for your projects during the community week, and how to make use of our Git version control. Awesome. All right, Suraj, do you want to go ahead?
Yeah, sure. Thanks, Patrick. So let me just start by sharing my screen. Awesome. Can you see my screen?
Yep.
Cool. So I'll talk a bit about transformers, and then we will go over the design of Flax models in transformers, how we can use them, and how we can write training script for those models so that we can train those models. All right. So what is transformers? So transformers is an open source natural language processing library, and right now it's one of the most popular library on GitHub. We have more than 45,000 stars and 800 plus active contributors, and right now it's being used in production in more than 5,000 plus companies. And at Transformers, our goal is to democratize natural language processing. And by that, I mean providing access to state-of-the-art models through a single unified API so that any user can easily access different SOTA NLP models and easily switch between those without having to learn different APIs or different frameworks. And recently, we have also started supporting other modalities like speech and vision. So we have integrated OpenAI's Clip and VIT, and the two very popular speech models like Web2, Vec2, and the Hubert model that Facebook released last week. All right, now let's dive into JAX, Flax, and how those models are implemented in transformers. Okay, so we'll talk a bit about PyTorch versus JAX, and this is intended to like show you the difference between how PyTorch models behave and how Flax models behave, and then why did we make the design choices that we made. All right, so in general, Flax PyTorch models are considered stateful. And by stateful, what I mean is when you define a PyTorch model like this, so consider a simple self-attention module which contains keys, values, and queries matrices and a logit projection. You define the layers, and when you define the layers, PyTorch also initializes their weights and stores inside the modules. So you can see in the diagram on the right that you have the layers and it also stores your weights. And when you are doing a forward pass and the backward propagation, these parameters are updated in place by the optimizer. So everything happens inside the module. But as opposed to that, Flax models are stateless. And by stateless, what I mean is when you define a model like this, model Flax in the Flax library, this definition usually just tells the module that what kind of computation to do and what kind of parameters to expect. So it does not initialize any parameters beforehand. So if you look at this diagram, this just contains the layer definitions, and it also stores like other metadata like shape and etc. But it does not initialize any parameters. And this is because Flax is based on JAX. And in JAX, most transformations like JAX.JIT or JAX.PMAP expect the functions that they transform to be stateless and to have no side effects. And this is because JAX functions are usually compiled. And when you compile a function, the side effect is only executed once, and the compile function will execute the same side effect over and over again so that the code becomes unreliable. All right. Now, so how to do when you do a forward pass with a stateful model, it usually looks like this. So your model already contains the parameters, and you just need to pass the inputs, which are here called input IDs. So the model takes the input, it has the weights, and it does the forward pass and returns you the output. Whereas in Flax, as the model does not contain any weights, it does not maintain any state, you need to pass it the inputs as well as the states. So which you can see here, the apply method receives the input IDs and the state. So the state is composed of the parameters and other variables like batch norm statistics and etc. So again, to explain the clear difference between PyTorch and Flax models, in Flax you need to pass your input examples and your parameters explicitly, and the Flax model does not maintain any state. Okay, now let's see how you can use Flax models in transformers. So if you look at this slide, you can see that it has the familiar transformers API. So the from pretend method, save pretend method, and the call method. So to initialize to load the weights, to save the weights, and to do a forward pass. So this looks very much stateful. So how do we handle the statelessness of JAX Flax if our model looks stateful? So that is taken care of by this class called Flax pretend model class, which is an abstract class, which kind of like a wrapper, which wraps the Flax module, which is written here as a module class. And it provides two important methods called init weights and dunder call, which takes care of initializing your weights when you initialize the model, and the dunder call method takes care of doing the forward pass by taking the inputs and the parameters. So the init weight methods calls the init method on the wrapped Flax module and returns the parameters, and then this init weight methods is called in the dunder init methods, and the parameters are stored in this self.params attribute. And then you have your familiar from pretend and save pretend methods so that you can easily load and save weights. Now, if you want to define your own Flax model that has this similar API, how can you do that? So we need to like kind of do 3 steps. First, you will write your Flax module the way you usually write the Flax code. So let's consider a simple MLP example here. We have 2 dense layers and we do the forward pass called dense layer, then ReLU, and then the second dense layer. So you define the Flax module. Then what you need to do is you need to create another class by subclassing this Flax pre-trained model class, and then you need to override the init weights and the dunder call methods. So in the inside the init weights method, you kind of give the RNGs which are required for like initializing the parameters and for dropouts and etc. And then you also give the input shape, because to initialize the Flax model's weight, you need to pass a dummy example to do the forward pass and to retrieve the weights. So we initialize our input, a dummy input here, we initialize the necessary RNGs, and then we call self.module.init, which takes the wrapped Flax module, passes it the RNGs and inputs, and returns the parameters, which are then stored in this pre-trained modules instance with, and then those can be accessed using model.params attribute. And in the dunder call method, you define all the attributes or all the parameters, the inputs that your model is going to take, and also the parameters that it is going to take. And so when you don't pass any parameters, which are by default none, the model will use the stored parameters, which could be randomly initialized or which could be loaded from the from pretend method, and then it just simply calls the module.apply method, which Flax uses to do the forward pass. So because of this, you can without having to use the init method or the apply method, you can simply call the dunder call and the model, and simply init the module as you init any Python object. Now, to actually define your module, what you need to do is you need to create another class called Flax MLP model. You subclass it, and then you set the module class attribute here. So which tells the pre-trained module class what modules to expect and what module to initialize, etc. So once you do that, your models will have the same API as with any other transformer models in the library. So it will have access to from pre-trained method, save pre-trained method, and then you could easily do forward pass by simply calling the dunder call method, which is called by default when you call the module instance. Again, the important point to note here is that this model is not an instance of nn.module. It's just an abstract class which wraps the the Flax's nn.module and just provides you convenient methods to work with. Awesome. So now let's see how we can train these Flax models in transformers. So to usually train any Flax model, what you need is a loss function that takes the parameters and the inputs and does the forward pass and returns the loss. And then you need also an optimizer which takes the gradients and parameters and then returns the updated parameters. And then a simple a train function which does the forward and backward pass. That is, it runs the loss function, does the forward pass, gets the loss, passes it to the optimizer, and returns the updated parameters. So usually a simple training example will look like this. So you define a method called a loss function, a function called loss function or compute loss, and it takes all the necessary states, which is the parameters, input IDs, and labels. Then we do the forward pass by passing the model the input IDs and parameters. Again, the important thing here is that when you are training the model, training a Flax model, you need to pass these parameters explicitly. As I said in the previous slide, Flax does not store any parameters. Then you calculate the loss, then return the loss. Then to take the gradient of the loss, we need to transform it using the JAX value and grad function. We use the optax library to use for optimization. So you just define what optimizer you want. So here we are using the SGD optimizer, and then you initialize the optimizer state by passing it the initialized params. Then inside the train function, again, you need to pass in the whole state, that is the parameters, optimizer states, any other RNGs if those are needed, and then the inputs and outputs, which are input IDs and labels. So the 10 steps then calls the grad function, which is by passing it the parameters, input IDs, labels. It then returns loss and grads. Then you just call tx.update, which returns you the updated optimizer state and updated optimizer states. Then you call apply updates by passing it the parameters and updates, which then returns the update params. So as you can see here, you always explicitly need to pass the parameters and the new states, and all the JAX function or the Flax functions returns you new updated parameters and updated states without updating in place. Then the train step returns this updated parameters, states, and loss. Then in the next step, we usually JIT the training step so that we get the maximum performance that is possible. If you are doing distributed training or for on multiple devices, you will usually use jax.pmath, but we'll explain those more in the docs because we won't get much time to explain it here. All right. So once you have your train step, then you can just simply write a loop and keep passing on your inputs. So here we call the train step method inside the loop. We always pass it the parameters, optimize the states and the inputs and the outputs, and then it returns us the new updated parameters and optimizer states, which we then pass again. So that's how our parameters get updated. Okay, so this is how we can like simply define a simple training loop for Flax models. All right, that's it from my side. Over to you, Patrick.
All right, great. I'm going to start sharing my screen now. Great. Okay, so I'm going to give you a little demo on how you can use the hub during the community week. So first of all, I want to explain a bit how the hub works. So here you can see we have models, data sets, and resources. And what you will probably do is to check out existing models. We already have a lot of models in the hub, and many of you will probably use pre-trained models, or at least check out the configuration of existing models when you want to train a model from scratch. So here on the left, you can filter by tasks. And then below here, you can filter by libraries. So for this community week, we should filter JAX because we want to see how many models we can use for JAX. We have 4,000 here. And then a lot of projects are also specific for a language. So here you can kind of decide on your language code. So let's say we're going to use some German models. We filter by DE, the language code, and then you can see all the models here. So then we could also search for a specific model, let's say BERT, in case you want to fine-tune a pre-trained BERT for your project. You can click on it, and then you can see all the information about the model here. So that's just in general how you can kind of use the hub to find a good model or a good configuration you want to use. All right, now let's demo a bit how you can actually use the hub during training. So we create this organization, which is called Flax Community, and we already have a lot of members, which is awesome. And it would be great if you can upload your model repositories to this organization. This, for once, this helps us to have a good overview, and second of all, we can help you because we can directly access the organization, and everybody can access all repositories, so you can help each other, which is nice. All right, let's do a little demo now. So we create a model, and we're going to create it under the Flax community, so under the organization, so everybody has access to it. And we're just going to call it Roberta base and then ALS. So what I do here is I'm just going to pre-train a Roberta on a very, very low resource language on the Oscar dataset, which is called ALS. So we'll just do that and then create the model. Oh, actually already exists. So it's called demo. Cool. So now you can see we've created this model, and by doing so, we've created a Git repository essentially. So this identifier now is a Git repository for for the project. And what we'll do now is we'll clone it. So we'll just copy that. So you can find here how to clone it. You need to install Git LFS for that, so you can upload the heavy model weights. And then you can see the link here. So essentially those two commands give you a Git clone. So now I'm just going to show how you can do this in your console. So we run this command, and we can see now that we've cloned the repository locally. So this is the project essentially. Now this is our project where we want to pre-train a Roberta base on Alemannic. And as you can see here, it's essentially a Git repository. So we have first commit, initial commit, we created it. And you can use it just like a Git repository, which is very nice. Now I've prepped some code. So in the beginning, what we're going to do is we're going to move the code that we need inside the repo so that we can track it. And you can see now that the state changed, and we've added a file that you can track. And we're going to run this, and this is just going to create a config for us. So as you can see here, it has created a Roberta for MaskLM config, a very basic one. And now we've added a file to it, a config JSON file. All right, then we'll also create a tokenizer. So I'm just going to run that as well. Luckily, the dataset is super small, so this actually runs quite fast. So what we do here now is that we train a new tokenizer, so a byte level BPE tokenizer on the small dataset. And it should also just take a couple of seconds actually. So it's already finished. Great. Now you can see we have the tokenizer.json file as well. And now what we want to do is we want to actually upload all those models. So here, so we can say add config, tokenizer. And now we add and upload all the files to our repo. Cool. Also, now we can start training the model. So we've defined the config and we've defined the tokenizer, so we can initialize as a random model from our config and use the tokenizer to process the data. So we'll do the same thing here. We'll move our scripts, the bash script, into the repository, and also the training script, and run that as well. This is going to take a bit longer, but essentially what we do now is we train the whole model from scratch. So the run, if I show you a bit how this looks like, this is just a bash script that runs the general run MLM flag script that we've uploaded to the examples folder. So you have access to that. For most projects that just pre-train Roberta or GPT from scratch, you can actually use these scripts out of the box. You just have to define the fitting language here, and then also the model type. Cool. All right. So this is going to train now. This is going to be pretty fast actually. But in the meantime, I want to show you what happened now to our repository online. So now you can see that we've uploaded the files here. So we have a Git history, as you have in our Git repository. As you can see here, and we've added the files, which is very nice. So you see exactly what happened. Config and all the files. And you can also go back to commits. For example, if you deleted a file by accident or whatever. And so that's very nice actually to kind of keep track of your work. And everybody in your team has access to this repository. So it should be very easy to collaborate on that. Great. Okay, let's see how our training is doing. Okay, still running. So it's so the beginning is always a bit slower because it has to compile on TPU. So you'll often see this in the beginning, that it seems to be freezing in the very beginning, but that just means that the code is being compiled. And now you can see it's very fast. So once it starts, TPU is actually very fast. So now we finish one epoch. You can see the loss, and now with the evaluation. And so what's happening now is actually that we upload both the weights and the TensorFlow logs directly to the hub. So we've defined this in our bash script here. We've added a flag which is called push to hub. And this allows you to directly upload the TensorFlow board traces and the Flax weight to the hub, which is very nice. And the cool thing now is that you can see this directly in our demo. So when you check out this repo now here, you can see there's a new tab which is called training metrics. When you click on it, you can actually see the tensor board live. So this is very convenient if you want to share your progress with other teams or with the organizers. You can take a look at your tensor board traces and at your logs to identify bugs or other things. So this can be very convenient. And most scripts, or actually all Flax scripts, they have this this push to hub flag right here, and we strongly recommend that you can use that so that you have access to the TensorFlow or the TensorBoard logs right away here. All right, great. I think that's it. And I'll stop sharing my screen. Great. So I think now we have some 5 minutes left for questions, so we can answer them. All right, maybe I'll just go through the chat. So how do we set up write access for team members? Yeah, so the write access is a good question. So because we give everybody access to the organization, which is called Flax Community, everybody has write access to all GitHub repositories. What we'd like to see is that team members kind of only write to their repo in the beginning, but then eventually when other teams want to help a certain member, then you can also directly write into other repositories which don't belong to your project or your team. So we think this is the best way of kind of sharing, collaborating as a community. Yeah, we kind of hope that people don't mess with other repos. So you shouldn't go into other repos and delete files. You'll be able to do this, but we keep track of the logs, and we can obviously revert this since we have a Git version control. Yeah, and it's a very good question. So we recommend to actually keep all the code that you have in this repo. So even if you use an official training script like I just did, we recommend that you copy it into the repo and upload it. Essentially, you should have everything that you need for the project inside this repo. So the model weights, thanks to Git LFS, you can upload this. All logs during training and all code that you wrote. So that's the best way for us to find bugs and to reproduce also your training runs. The only thing I guess that you shouldn't have is the other data files. So if you have a data set of 100 gigabyte, then maybe just leave the code in there that downloads the data, but don't add all the data files into the repo. Great. Is it possible to train with multiple V38s for the same training? I am not sure actually. I haven't tried that yet. I think it's going to be hard because it's different TPUs. Sorry. Cool. Yeah, then information about pre-training GPT-2. We have a very nice collab. So if you go to the official Flax example folders and then to the README, you can see there's this GPT collab, which explains everything step by step. So that's very nice. Then we have to VEC two questions. So we have to VEC the inference is fully tested. So inference works. You can try it out. So you can transcribe speech with existing models. The pre-training script is also tested. It works. I haven't done a complete pre-training yet, but it should work. So I did some integration tests with the official FAIRSEC code. And all right. Can we pre-train the BART model from scratch? Yeah, well, you can. We don't have the official kind of BART pre-training as a script right now. We have an official T5 pre-training script, but not the BART pre-training. So BART used a slightly different pre-training algorithm than T5. So we don't have that yet. We recommend actually using T5 if you want to pre-train a sec to sec from scratch. But we have a BART summarization script, so everything which is fine tuning is should be very easy for all kinds of sec-to-sec models. All right, I think I'll give it back to Susanna. And
that sounds great.
yeah.
Thank you for taking over the questions. That was great. Yeah, cool. Thank you both for your talks. That was really great. Good to see a demo. I think that helped a lot of participants as well today. We did have like a few more questions, related questions, how to get started with TPU VMs, cloud TPUs. We had a really great talk yesterday by Sky, who introduced that a bit, so you can watch that as soon as it's online. And Suraj also shared the docs for a user's guide to TPU VMs. Awesome. That was our first talk. Thank you so much, guys. That was great. And I think we can move on to the second talk of the day. Sabrina, whenever you're ready, you can start sharing your slides. Maybe I'll introduce you. Meanwhile, Sabrina is a PhD student at the Johns Hopkins University, and she's also at Hugging Face part-time. And she'll talk today about how to go from stateful code to purified JAX and how to build your neural net framework. Super excited to hear about that.
Okay, awesome. Yeah, thanks for the introduction. That's basically what I'm going to be talking about. How do you actually make that step from like reading like the JAX intro docs and being like, okay, so this is like NumPy but cooler or something, to building frameworks like we've seen with Flax yesterday and today. So I'm just basically going to jump right into it. This is from a paper that I wrote a few months ago. We were like doing some k-means clustering, and I was like, hey, we could just put this on the GPU with JAX, and voila, you get great savings. It's fast. Hooray. I think someone had this tweet yesterday in their talk, and this is the one time Jeff Dean retweeted me, and I was like, oh my God, Jeff Dean. And you might also have used JAX for getting an easy way to do like autograph for functions. So this is a kind of convoluted example. There's definitely no need to look into it in detail, but if you know what reversible jump MCMC is, you know that you need the Jacobian determinant of the diffeomorphism that's involved. And you know, basically fancy gradient taking diffeomorphism, well, I define a Python function, and then JAX really does all the rest for me. I'm like looking at the Jacobian right here, and then take its determinant, the absolute value, and it just very nice and easy. It makes sense. Like this is kind of what it feels like JAX's gradient taking is made for. It's kind of like, yeah, you have a function. It depends on some arguments. I can get the gradient of the scalar output with respect to one of the arguments, by default, the first one. Great. But this is quite different from what we might know from, oh yeah, and also speed. This is quite different from what we know from frameworks like PyTorch. So in PyTorch, or also like eager TensorFlow, we built up our execution graph, so what step by step, we say this is a tensor, and then a new tensor is created, and so on. And what happens when we call dot backward is that this whole graph is traversed backwards. We can also call this tape based. It's like kind of keeping track on a tape what happened and then going back down the tape. And okay, we get gradients this way. And that's what, when I started learning about JAX a little over a year ago, that's what I was familiar with, right? So how do we go from this to what's happening in JAX, where functions are pure? I remember someone asked about this in the previous talk, and that's going to be great because we're going to be coming back to it. When a function is pure, like it has these arguments, W and X, and then returns something. And then if we do the gradient thing, it basically gives us a new function that's also pure. Again, we'll talk about that later. And now it gives us the gradient of the output with respect to, in this case, the first parameter, because we didn't specify anything else. And so that is how we could get gradients, I suppose, right? You see that in this case, the gradient is this number 42. Okay, fine. But this is kind of small and silly, and like, how do I train big models with lots of tensors, complicated functions, and things that aren't pure? So that's what we're going to be doing in this talk. Or put differently, how can weights and gradients be stateful if our tensors can't be mutated? For those who spend too much time online like me. I'm going to say in the very beginning, this talk is based on a blog post that I wrote in March 2020. So you might say, okay, wow, that was a long time ago. Is this blog post still relevant? Like, isn't this kind of outdated? And the good answer is absolutely not. It has never been relevant. It has always been a silly little teaching experiment, more so than a canonical thing of like, oh, this is how you should do things. The good side of that is it will never not be relevant. And I think that the ideas in there will hopefully help you get a sense of why the frameworks that you've seen yesterday and today look the way they do and what's really happening in there. So what we're going to accomplish is explicitly not building any great models or beautiful frameworks. We're not going to be idiomatic and elegant. My code is going to be nasty and messy in some parts and definitely not safe for work. There's also not going to be any batching and distributing and compiling with JIT. And you might say, wow, okay, so there's going to be nothing in here. What we are going to be doing is really taking a small example, in this case, linear regression, doing it statefully in PyTorch, and then being like, wow, how do we transfer this when we move to JAX and try to be pure? We'll have a little aside. It's like, oh, this is another way you could do it that hasn't really panned out. And then basically built up what these frameworks that we see are doing. Let's get right into it. This is what a module in PyTorch looks like. If you have never coded PyTorch or either TensorFlow and this is your first neural net framework, wow. Okay, cool. But otherwise, probably you've seen some of this, right? There's like, we've seen this in the talk just before, modules that own their weights. It's like, this is just a tensor and we give it some initialization. And so the class now owns its weights. It can use it when building this execution graph, when compiling this tape. And then when we use this, so this is the two steps we've just seen before in a training loop, we can do loss.backwards, which writes the gradients next to the tensors, and then update each parameter's data by, in this case, subtracting the gradients. So this would just be vanilla SGD. And this means that, yes, there is this one module, it owns its weights, and we mutate those things. That is a little bit of a big example. So at this point, I'm going to switch to a notebook, and I hope everyone can see this. Let me know if not. This is also the first time that I've given a talk with a notebook, so this will be super fun. I'm very excited. Let's actually look at a much simpler example. So this is something we are just defining 1D linear regression. You know this from school. There's going to be like a weight and a bias, if you want to call it that. And the formula is pretty simple. The weight multiplied by the input plus the bias. For training, I'm going to define this function for root mean squared error. Again, pretty standard. We're looking at the results. How far is it off from the goals, the y's, square the whole thing, take the mean, take the root. Okay, so far so good. And create this as a class. So this is just standard PyTorch stuff. I can show this. This works. Here, let's predict it from 3.0. And since we've initialized it to 0, we should expect 0. Yep, 0 comes out. We see that there's a gradient function associated with it for the whole tape-based shenanigans. We can also test our other function. If we define our training pairs to be that 3 should result in 7. Okay, there's a loss of 7. That makes sense because 0 and 7 are 7 apart. So far, so incredibly boring. It's going to get worse. We're going to also write an SGD loop in PyTorch. I've given yet one more training example, so we're not completely underdefined. And then, yeah, you get the loss, do it backwards, you update your parameters, you zero your gradients, never forget that, and then see what happens. And we see that as training goes on, yeah, we get kind of close to the 7. Now, this is pretty poor SGD, so we're not really hitting it nicely, but you get the idea. This is actually doing what it's supposed to do. So what could that look like in JAX? Again, we could start with something that's very similar. We have a linear regressor class, has a weight and a bias, it owns them. I could make these JNP arrays if I wanted to. It doesn't really matter. We have a prediction, we have this thing. It's literally the same thing, except I replaced torch with JNP. It's so nice that we all somewhat standardize on the same thing. This is great. And now I have a thing, and it's great. Yep, this is on CPU. No worries. Let's do the same tests again. Yes, we get 0 and the loss is 7.0. So that's nice and all, but okay, now what? How do we train things, right? Like we have a loss, but we can't call dot backwards. We need to have some pure function. If we go back to this, some pure function that we can sort of invert or take the gradient of. So where does this pure function come in? To talk about that, let's actually do a little interlude on purity. I'm going to even give this its own headline. What is purity? Here are 3 examples of functions, 2 that are pure and 1 that is impure. A pure function, generally the idea is that, well, it kind of takes some values and it outputs some values, and it doesn't interact with anything outside the function. It doesn't mutate anything, right, except for what's contained in itself. And it doesn't access anything. It wasn't explicitly given as a parameter. So this function is clearly fine. It only gets an x, it only accesses the x, it doesn't mutate anything, it returns something, great. This function, on the other hand, in Python would not be fine because the list XS that is being passed is actually mutated. And so if I were to call this, we can just do this. Impure function 1 XS, let's see, find it like that. Well, let's call it L, just so we're not confused with the other code. You can see that the list after calling this function is now changed. So this function is impure. Okay. This, on the other hand, would be fine because stateful mutation inside the function, well, that's no problem, right? So this would return a new list that in this case has these changed values, but the original list, importantly, is still the same. So that's pure. Give you some more examples for impurity. This is another kind of classical one. If we have some global state, like in this case, number of executions, and the function mutates, that is very clearly impure. But even just accessing the state is impure. The reason being that if I call impure function 3 on the value 3, okay, well, I got a 0, but now I call it again. We see that this has changed, so that sucks. And so this is already giving us a sense of what is going to be an easy check for purity, and is, I think, my favorite mnemonic for this. If the function could just be a lookup table, or you could cache the function and nobody would notice, except for that it might be faster, then it's pure. And so that, I think, is a great check to actually check if something is pure. If you can replace it with a lookup table, and this seems kind of outrageous, then it is a pure function. And you'll see that this is true for those things. We could replace those with a lookup table, right? We might give this beautiful Python decorator for caching, and nobody would notice. But we couldn't do it for these functions. Finally, last classic examples. If you use I/O, like you print things, you get user input, or you try to get the current system time, those are all impure. And it makes sense because you couldn't cache these. These could change all the time. I'll give you one thing. If you paid attention during the previous talk, you kind of know why this one isn't impure. And I would like to just someone shout it out in chat. I should actually open the chat window, shouldn't I? Awesome. Yeah, just shout out in chat, why is this function impure? What's wrong with it? Something about random numbers, right? But yeah, so exactly. So this kind of violates kind of both sides of this. For one, it mutates the global random state because it advances the number generator. And it's not reproducible in the sense that if I call this twice, it's just not going to give me the same example. So that's another classic impure function. I also should have probably looked at the chat a little bit earlier. But one thing that is really important to me, this is not Comic Sans, it's Comic Code. It's my favorite coding font. It's beautiful. Okay, that aside, let's go on with this then. Let me move the chat over here. Cool. So how do we build a pure function for training? Okay, this is kind of aside is now over. To work. We could build something like this. So this is a loss function that uses our linear regressor class. It sets the weight and the bias and then gives us the error for the data. And you see that I explicitly pass in the parameters here and set them like that. It's a little ugly and I need to enumerate all the parameters. Definitely not something we want to do. But I mean, I guess it works. It gives us the right loss. And importantly, we could actually train with this. So again, use the same training data. And now we can calculate the loss with this loss function. And what we're going to be doing here is this. Maybe I should just show this in isolation. If we do JAX grad on the loss function, it gives us a function, right? And we could call this on on our data. What did I mess up? Oh yeah, I need to pass in W and B. Let's just say 0. And it would give me a number. What is this number? It's the gradient of the loss with respect to the first parameter. But we want the gradient with respect to both parameters. And so we can pass in argnums. And so it gives us both these gradients. Cool. So that's what we're writing here. These are the gradients. And then again, just apply them to these weights that this module owns. So this is kind of a haphazard PyTorch direct implementation, but you see it does train and it gets the job done. So cool, good for us. I hate it though. I really hate that I have to put the W and B in here like that. And we probably want to do better. So let's get rid of this. I don't like this class anymore. We're going to do it differently. Instead, we're going to have all our parameters in a dictionary now. And you've seen this in Flax and other frameworks. That's really how it works. It's dictionaries, it's frozen dicts. This is how it's going to be. And the beautiful thing about this is that JAX is able to deal with not just scalars or vectors or lists or tuples, but also dictionaries as arguments. And so now this is basically the same as we've written before, except we didn't have to write out W and B up here. We just did the params and then access them here, set them. Otherwise, exactly the same thing. Why is this different? I'm guessing because we already trained. Oops, this should. Wait a second. Why is this different? Oh, sorry. Yeah, because we have these complicated examples instead of the simple one. All right. So far, so good. We can again get gradients. If I type this in, just out of curiosity, what do you think is going to come out? Feel free to post it in chat. What is the type of gradients? What is this going to be? It's the gradients of that loss, the scalar, with respect to the first parameter. That's a dictionary. Right, it's a dictionary. And it contains the gradients for the parameters. So now we can apply them like this. Okay, sure. And the loss has gone down. Okay, that's good. Loss go down. Always good. Love to see it. But we can do something a little bit nicer than enumerating these. And that is we can just combine these two dictionaries with a tree map is what it's called in a tree multi-map is what it's called in JAX. I'm not going to go into too much detail, but basically it does what you think it does. It takes the two dictionaries and for all the keys that match, combines them using a function. And this function in this case, I've written something incredibly simple. It just takes the first value and subtracts the second one. So that's exactly what we want for an update. And so if we do this, yeah, the parameters are going to change. So this is our new my parameters and the loss has gone down yet again. Hooray. And with this, we can write a training loop that is not too terrible. Like this is actually not awful in my opinion. We get the loss, we do the gradients. We just have this my params dictionary. We update the parameters and off we go. And this is a little bit awkward, just to see that we can get close to the right values, and we are. So bear with me. We're going to make this a little bit nicer too in just a second. Okay. So far, so good. Everyone's still on board. We have taken this example and kind of translated it to something in JAX that is not terrible by making use of the fact that we can have parameters and dicts. Okay. So if you want a little break, this is the time, because it's time for an aside. We're going to be doing something that is really fun and that I think is somewhat obvious to do, which is why I think it's fun to cover it. And that is, we're going to make this a little bit cooler, and instead of dictionaries, use our classes as PyTree nodes. What do I mean by PyTree nodes? That's really what I was saying, that JAX can accept scalars, vectors, lists, tuples, dictionaries, because all of these are registered as PyTree nodes. And so we can use this tree multimap on them. And the cool thing is we can make our own classes PyTree nodes as well. So we can take our regressor class and define for it two functions, flatten and unflatten. And what they basically do is flatten takes a regressor instance and converts it into this tuple of leaves, which contain the actual numeric data, the scalars, the weights really, and some auxiliary information. In this case, we don't need it because this class is dead simple. And unflatten, which does the same thing, given the auxiliary information and the leaves, gives us a new instance of this regressor. So one thing to be careful, the order changes. This is incredibly sad, but alas, such is baggage from the past. Either way, this is not too terrible to write. And once we've written this and registered this as a PyTree node, we can now do cool things like this. Our last function can now actually take the regressor, the class, as an argument. Okay, so again, we get the last we want, cool. I'm gonna ask again. Now, we're gonna do gradients with respect to the first thing. What is it we're gonna get? Post it in chat. What is the type of gradients gonna be? This is kind of, it is a PyTree node, but it's a very specific PyTree node. Gradients is going to be a regressor. It's going to be the class that we want. And its weight and bias is actually going to have the gradients in the leaf. Exactly, Kevin. That's exactly what's happening. So we can look at this. Yes, it contains the gradients. So this is cool. And you can imagine, yeah, what's happening is that this is just being by JAX, this is being flattened. So it's just a bunch of scalars. Magic happens, and then it's being unflattened again and returned to us as a regressor. And now, again, we can just do the tree multi-map thing and combine our regressor that holds the weights with the regressor that holds the gradients. And voila, loss goes down. So this is cool. And I think this is an incredibly kind of appealing and intuitive way of doing things. And if you think the same way, well, I got something for you. You just add a little bit more magic, namely something that writes the flatten and unflatten logic for you, so you don't have to write it, by doing type annotation magic and some hijacking, just like initialization stuff that we're going to talk to later. And you get this like Sasha, Rush, and I tried to build last summer, and we got a little bit into it. It's basically runnable. We kind of gave up once we didn't really know how to implement batch norm because statefulness. But check this out if you think this is an interesting approach. So that's kind of taken this idea further. That's all I'm going to say about this idea. This is the aside over. We're going to go back to our regularly scheduled programming, namely the dictionaries, because that's really what most of the things, most of the frameworks are using. And we can make this a little bit nicer and introduce another cool concept that is really going to drive home what's happening in frameworks like Haiku and Flax. So I'm going to do something. I'm going to, first of all, go back to my slides and say what we want is we want to purify code. What do I mean by this? We really kind of want users to be able to write stateful methods like we did in PyTorch, because it is nice to just say self.w plus something and it kind of works out. And we would like to have a framework that purifies these functions, that creates things like this loss function that we manually created. And how that's going to work is like this. This is kind of what we want users to be able to write. To have a region like forward or call these weights and access them. And that makes this function impure, so we cannot call grad on it, which sucks. And the trick we're going to do is we're going to wrap this function in what I will call a purified function. So the user writes the same function as before. It accesses W. This is not cool. But we can create a new purified function that also takes W as a parameter. And first thing, sets that to be this value here that's being accessed. Then we can call a user function. So the user function says, oh, I have a stateful class thing, but joke's on you. We just set that. We just set it from the parameter. So no information from outside this purified function was actually accessed. This is great. We also remove it afterwards, just in case any trace, take nothing but memories, leave nothing but footprints. And we return the results that this messy, impure user function created. And so this function, purified f, that is going to be something we can totally call grad on. Okay. So a little bit more specifically, this is what we're going to be working towards. This is the tiny framework that I'm going to be building up in the remainder of our time, where we're not quite using self.w. We have this method called self.getParameter. Okay, fine. But I figure it's close enough. We also give that its initializer. So this is similar enough, at least, to what we saw in PyTorch. We use it as normal. So this is great. And down here, skipping the magic bit in the middle for a second, what we want is we want to be able to get initial parameters without having to write them out like we did before. And we want to be able to use those parameters to call this purified function, get its gradients, get the gradients, and update as before. So just to be clear on this, the benefit of this over what we've seen right here before we went to our little aside, sorry, let me just get that up again, is that we didn't have to actually do this. Okay, we already did that with the tree map, but we didn't have to explicitly enumerate parameters. So that would be nice. And the key ingredient is going to be this bit of magic that I'm going to call purify. And that's going to take this impure function and return a function that is the purified version, and a function that initializes the parameters and gives us this initial dictionary. And if you paid attention, you already know where this is going. This is apply, and this is init in Flax and Haiku. But okay, how do we build that up? Let's implement this step by step. I realize we're a little bit strapped for time, but I think it's going to be fine if we take this, because I think this is really the core of what we're going to get at. Let's implement this little flowcharty thing that I made in code. So I have, of course, already done this. So this is what it could look like. Again, this is our impure function. I've used the dictionary already here, but the idea is the same. The parameters are none, and the purified function takes parameters, sets the parameters, calls the messy user function, which of course uses self-params, but joke's on them because we set that just now. And then we zero out the parameters after and return whatever the user function gave us. This doesn't deal with the initialization yet, so okay, we specify that manually. But we can call this, I'm going to use JAX value and grad in this example because it is what you probably want to do. And so we can get loss and gradients from this. Again, using it exactly as before, except I was lazy and used this function because less writing. And you see, okay, yep, the loss is as it was, we get the gradients, and now we could tree multi-map those gradients with our parameters. Cool. So this is the idea on this specific example. But if we want to build a framework, of course, we're going to have to do a little bit of abstraction. So I'm going to put right here, I guess I'll have to zoom out to make it fit, what this class, I hope you can read this a little bit more. Okay, fine. What this class is going to look like. So this is going to be our base neural network module. It's going to have the parameters as before. And we're also going to have flags that say, are we running in pure mode? Are we running in initializing mode? This is going to be the get parameter. And so if we are running in pure mode, just return the parameters. If we are running in initializing mode, then set the parameters to something that the initializer that we specified gave us. And so this way we can now create these two methods that they both similar, like kind of do the same thing. First, set the flag so that getParam knows what it has to do. And then for initializing, we initialize the parameters to an empty dictionary, call the messy, annoying, I'm sorry, yeah, something wrong with my connection. It has been a bit messy all day. I hope it's still getting through somewhat. What we're going to be doing is calling the messy function. It sets the parameter using the initializer up here, and then we're going to take it, zero it out and return it, so that getParam knows it's allowed to return things. Parameters using this thing, again, like jokes on the impure user function. It thinks it's having side effects, but it doesn't because it's running in our little sandbox. And so set this to none again, return the flag and return the result. And then this gives us the two functions. And this is a bit fast, but I think if you go through this together with this picture, it'll hopefully make sense to you. So what this allows us to do now is doing this here. And so this is finally the purifying regressor as we wanted. It is inheriting from our flat fancy module we just defined. And you see we write these nasty impure functions that say, I want to get my parameter and I want to initialize things. We have RMSE, we have predict. And then this is exactly the interface that we wanted. It is creating this purified function and this initializer function. We can get initial parameters just to show that this actually works. Oops, I should have executed that cell. Okay, initial parameters just like we wanted. It's so nice. We didn't have to specify this. Yes, win. And we can get the losses, do the gradients and update. And you see that, yes, loss goes down. This is still the same as we wanted, but you see that we're getting more and more comfortable with every little bit. For completeness sake, the final training loop might look something like this. Here I purified the prediction method. I, in this case, don't care about the initializer because I already have the parameter dictionary. And so now the training loop is very, very concise. I get the gradients from my purified function, I update it, and I want to print how well I'm doing. How close am I getting to the 7 that I want? And you see, again, training works fine. So that's all from the notebook. The last thing I'm going to leave you with is that, as I hinted at, what we've done is basically re-implement what all these fancy frameworks have been doing. And so at the time I wrote this blog post, Flax had just like sort of come out, and it was like, this was pre-Linen. And so the most mature kid on the blog was Haiku. And you see that what we did is very similar to a Haiku implementation. In particular, we inherit from a module base class, as does Haiku. We have a method to get parameters, as does Haiku. And we have this purification, which Haiku calls transform. And again, it takes an impure function and then gives us an init and an apply function. And that's exactly what these functions were for us. Also this morning, I was like, hey, actually, I wonder, now that Flax is linearly written, it looks very similar to, which we didn't talk about at all because of the worms, but same idea. And indeed, Flax now looks very similar. The one thing that's kind of different is we have this NN compact thing. You can look into that in the Flax docs for more details. But other than that, yep, inherit from a base class. Yep, have this function that gives us our parameters if we want them to, and also has the initializers in there. And yep, have an init and an apply. So it's exactly the same idea. And if you understood what we were doing while we were building this up, then these interfaces of Haiku and of Flax Linen. If you're interested in more complicated examples and maybe a little bit more deep through this again, do check out the blog post. Yes, it is a year old, and I've changed code things a little bit for these slides to make it nicer and more concise, but I still recommend it all the time when friends want to learn JAX. And yeah, follow me on Twitter because the number go up. It's always good. And hope that was useful to you all. I realize we're a little over time. I'm sorry for that. I don't know if we have time for questions, but also you can email or DM me on Twitter if you have questions, or message me in the Slack. Always happy to answer.
Awesome. Thank you so much. This was so much fun. Love the interactive part. And we had a lot of hearts and thumbs up for your notebook and for the font as well. So super cool. Yeah, some people asked if you may want to share the notebook. Your blog post is first out. Yeah, that would be great.
Yeah, I was going to mention that.
Yeah.
I'm going to link the slides and this little notebook and the recording once it's up at that blog post, and probably tweet about it or something. Yeah, absolutely.
Perfect. Thank you. If you have a little bit of time, please do stick around. We had a few questions in the chat, and
awesome,
later on, I'll anonymize the chat, and maybe we could make it available as well. So if you have a bit of time, please do stick around. Yeah, thank you so much. We're a little over time, but I think it's totally fine. I would like to welcome our third speaker today, Mostafa Dehghani. You're here, all right? Mostafa, can you hear me?
Hey, yes, yeah, I am here.
Oh, welcome. Thank you so much for joining us today. It's the third talk today we're going to hear, and super excited. You'll be talking about benchmarking transformers, and we're very excited to hear more about it.
Yeah, thank you very much. Thanks for having me and for the opportunity to talk about the long-range arena, the benchmark that we actually built about a year ago. Do you see my slides, by the way?
Yes, it's good.
Okay, awesome. Okay, great. Okay, so I wanted to basically talk. It's going to be a bit different from the previous two talks, and it's going to go a little bit. The point is that this whole project was implemented, like all the baselines that we implemented were implemented in Flax, and we really enjoyed it. It was actually a blast to have the chance of having like JAX and Flax around when we decided to do this. Otherwise, it could have been like very like difficult and much harder. But in general, it's about the like benchmarking efficient transformers and variant that they are actually introduced for making computational decrease to introduce to decrease the computational and memory cost of transformers, especially when they're dealing with long sequences. So I think I don't need to say anything about this slide. Transformers are everywhere. We're going to have also some talks tomorrow about like transformers on vision. Every day we hear like a success of transformer in different applications. It seems that they are actually the way to go, at least in short term or midterm. For future, we don't know, but I think they are also inspiring a lot of architectural contributions that are coming on top of transformers. So what is happening here is that basically we have this self-attention, which is the main or the heart of transformers, and basically what we have is that we have this token-token interaction, which has the quadratic complexity, and then this is a this can be an issue, especially if we go to longer sequence lengths. So if we go to sequence lengths longer than like 1K or 2K or 3K, this might actually slow down the whole things a lot. The point is that we have a lot of problems on many domains that we really need to deal with long sequences. Like when we want to work with long text documents, when we want to compare them, retrieve them, model them. If we want to actually work with images, if we really want to actually work on pixel level images, like ImageNet is 224 by 224. It's already a super long sequence. Even with the patch-based processing of images, for some application, we really need small patches or overlapping patches. Or when we actually work with megapixel images, with patch-based processing of images, we still deal with a super long set of sequence of tokens. On videos, it's also, again, obvious because we also have this time dimension. So if we want to process videos or like patches extracted from a frames of videos, without any factorization, again, we are supposed to deal with long sequences. And the last one is also pre-train sequence modeling, which, protein sequence modeling, which is also the motivation for some of these efficient transformers that they came up. And there are actually many different variants of transformers coming up during past almost 2 years for solving this issue. In particular, the quadratic cost of self-attention when they are supposed to process long sequences. So we actually started with writing a survey. We actually started studying these transformers, and we wanted to understand how these variants are related and how they are how they basically can we somehow introduce a sort of taxonomy to group them into different groups and understand how they like how these different form of transformers came out with respect to each other. And we wrote a survey on that, which I think it's also one of the really nice one in terms of like grouping these different transformers. We also talked about all the details about these different models. We also discuss how the memory and like computational cost of each of those and compare them. We also talk about like the constraint that they have. Some of those, for example, are not applicable in decoding. There's no straightforward or sometimes even impossible to do the masking of the future. And basically we group all these into 4-5 different groups. This low-rank kernel models, fixed factorized random patterns, learnable patterns, memory, and recurrence. And this is a bit old. I think if you want to start adding the transformer that they came out during past year, probably they're going to be like 10 more different ideas in this figure. But I recommend actually checking out the survey. That was actually one of the, I think I never actually wrote a survey, but this one of those that I really liked, and I think it was also pretty well received by people who are working on efficient transformers. Super informative for comparing different models. And then the question is that, okay, you talked about that, but how do they compare in practice? How we can actually empirically check if they which one is better? And at the time that we were proposing long-range arena, I think still there's no specific benchmark for measuring the quality of these transformers when they've been used in long sequence modeling problems. And then the goal was, can we basically find out a set of tasks that basically in a unified way we can measure their performance, as well as the cost of using each of them in terms of memory usage or throughput. And then we started actually thinking about, okay, what do we want from this benchmark? First of all, we want it to be a general benchmark in a way that at least we include tasks that like at least the set of transformers that the efficient transformers that we had at that time are applicable on that. So we stick with, for example, encoding only tasks, so no decoding or language modeling. The other one was simplicity. We wanted to basically have a setup for every task that is simple, so no other factors like data augmentation or pre-training is involved, to basically have a pure setup for comparing transformers without having other factors involved. We wanted these tasks to be challenging, so they should not be, so we didn't want to actually go for a task that the transformers are working like with 99% accuracy, but something that there is still room for improvement. And we wanted them to be long, which was actually the key point of this whole benchmark. And we wanted to also have these tasks probing different aspects of the like quality of the model in terms of, for example, how they are good in terms of capturing the relations or hierarchical and spatial structure, how they do in terms of generalizing over length, how they do for modeling, for example, transitivity, and different things that you can actually assume when you're dealing with long sequences. And also we wanted to stay in a setup that is as accessible as possible for like people who are especially at academia. So you don't need to have industry level computing resources to be able to evaluate your transformer. And then we ended up with 5 different tasks. We actually had, I think, 10 more, But we started actually pruning a bunch of them, and then we ended up actually with these 5 tasks because they were somehow representative, and there's less redundancy in terms of like the aspects that they evaluate. And the first one is long document classification, which is basically IMDb, but with a character level setup. The other one is long document retrieval or matching, which is ACL network, where we have 2 inputs and we are 2 documents, and we want to basically match if they're related or not. Each document has 4K lengths if we go character level. And then the other one was list-ups, which is a synthetic data set for logical operation. And then this in some way kind of assess the ability of models in terms of modeling hierarchical structure for solving such a nested logical operation. And then the other one was image level, pixel level image classification, which is simply CFAR, but the model is supposed to work on a set of pixels instead of patches or any other thing. So the sequence length is pretty long. And also generalization is super hard in that. And the other one was also Pathfinder, which I have 2 examples of that, which is basically an image task where you really need to have this global receptive field or having some sort of recurrence or some sort of like features in the architecture that is able to capture the transitivity. And the task is that you have these palettes, and then you have 2 points, and you're supposed to and there are like some lines, dashed lines in that palette, and sometimes these 2 points are connected, and they're also noisy, like basically noise in these palettes, and sometimes they're not connected. So for example, in top example, it's a positive example, and the bottom one is a negative one. And this task is actually rooted from some cognitive test, which is also done on human cognition and perception. And if you, for example, feed this, there is no way, for example, convolutions with local receptive field can solve this. That there should be some sort of, as I said, either a recurrence, or you need to see the whole patches or whole pixels in one go to be able to see if these 2 points are connected or not. So that's also because it's also generated synthetically. We had 2 versions of that. Like one was basically 4K, and the other one was one was 1K sequence length, like 32 by 32 pixels, and the other one was 16K, which was a extreme version of Pathfinder. We also wanted to know that, okay, what is the characteristics of each of these tasks? So we did some simple calculation in terms of if we apply a normal transformer on this task, what is the kind of like the attention span of a normal transformer for solving this task? And the attention span or mean is actually defined by the mean distance between the query tokens and every key tokens scaled by the attention weight in all heads and in all layers. So we just like collapse all these information into a single number, and then we noticed that for some of these tasks, you really need to basically attend to tokens that are really far from each other. For example, in case of list retrieval, you basically have your model in average is actually attending over tokens that are 1,000 position away from you, which also shows the point that I don't want to say that you need, but it's actually a proxy for the model actually is using this global receptive field for solving this task. So maybe it is also needed in the underlying solution that you are supposed to get to. So we evaluated 11 different transformers against these LRAW tasks: local attention, sparse transformer, longformer, leanformer, reformer, Sinkhorn transformer, synthesizer, big bird, linear transformer, and performer, as well as the transformer itself. And as I mentioned, we implemented all these in JAX and Flax, which was pretty nice, because I can imagine implementing these in other frameworks can be a bit more difficult or challenging. But this is actually the like basically scores on every individual task, in every individual like candidate model that we had. And for example, we had this LRA score, which is the average over all these tasks, which you can say that the winner is here Big Bear in terms of the performance, but this is not the whole story. We also need to check out the throughput, which is we measure that with the step per second, and also the peak memory usage in terms of, for example, gigabyte. And then you can see that, first of all, back to the performance, you can see that like different models, they are, like the top score in each task is from different models. There's no like absolute winner that actually gets best score in all tasks, which kind of shows that there are some inductive biases introduced by the way that they want to tackle this computational cost problem, which also affect the way that they converge to a solution. So they are actually converging to different solutions. So it's not just controlling the computation, but also introducing some inductive biases that is good for some tasks and is maybe not a good idea to have that bias in other tasks. Also, Pathfinder X, we basically failed to generalize to the test set with any of these transformers. So some of them are doing basically a good job on the train time, but none of them were able actually to go away from the random score on the Pathfinder X, which is we wanted to remove it, and then we decided, okay, no, let's keep it. Maybe someone actually comes up with a model that does a great job on this, so let's have it around. Back to the speed or computational cost and memory cost, we plotted all these models in this plot where the x-axis is speed, the y-axis is LRA score, like the quality of the model, but compressed in one single number, which again, it's a bit, it's not a good idea to do that. But, I mean, like we just wanted to have one dimension basically introducing the or representing the quality of the model. So we just averaged over that, all the tasks. And then you can see that basically what we have here is if a model goes to top right position, it's actually a really good model, which means high speed, high performance. But there is always a trade-off. So we have some models, and by the way, the size of these nodes are basically the memory that they use, or the peak memory that they use during training. And as you can see, there's always a trade-off. And then, for example, Big Bird was the absolute winner in terms of not absolute winner, but like winner in terms of the LRI score. It is pretty slow compared to others. And for example, something like local attention, which is kind of fast, it doesn't get you a good result. So it really depends what you want to do. So if you're looking for the answer to this question, that which one is the best one, I think it's complicated. But in general, we observed that basically between all these models, the linformer and performer and linear transformers are they are basically offering a rather good compute performance trade-off. And interestingly, they all actually are from this kernel and low rank group of methods that they want to tackle the problem with long range long sequence modeling. I just wanted to say that the code is open source. The data set is available. You can actually go to the GitHub page of Long Range Arena and then download the data set, and all these models are also implemented there. We are receiving emails from different people and from different research institutes and different companies that they're actually working on new ideas for transformer models. And this is super exciting that LRA is actually giving them the opportunity to directly compare these models with an existing set of existing models. And also, it's also nice that people see this as an opportunity to basically think out of the box or I actually really like this tweet from Oriol that like basically think out of the circle to come up with something that is not really in this paradigm. Maybe someone comes up with an idea that is solving this problem, or solving the complexity of the self-attention using a completely different idea and completely different method. And we are actually looking forward to see a model right here, up here, and which is super good in terms of the score, and also super fast, and really a small one, and also really memory efficient. I think that's it on my side. I think I just left 7 minutes for questions or comments.
Perfect. Thank you so much, Mostafa. We had a lot of great feedback in the chat when you started talking about excellent work, really fantastic work. And somebody asked if the code actually is open source, and you just confirmed, yes, everything is available.
Yes. Yeah. The code for the like the input pipeline for all these data sets, the data that we generated, and also the implementation of these 11 models are all available in the repo.
That's great. We did have a few questions in the chat. Maybe you want to have a look at it, and I'll read maybe some of them to you. One of them was if the learning problem is harder in terms of like sample complexity, statistically speaking, not speed-wise, for problems with longer range attention.
Sorry, I missed the question. So the question is that why we have difficult time learning problems that they are dealing with long sequences? Is that the question, or
yeah, in terms of sample?
Okay, so
yeah.
Yeah, okay. So the point is that yes, it really depends on the nature of the task. You know, I mean, we cannot really compare a sequence like a list of tasks or a task that is basically on answering the question for given a logical operation when the sequence length is 4K, and compare this with a like document matching with 4K. So like sequence length is equal, but they completely they require completely different type of solutions, or different things are really important for solving these problems. I think in LRA we wanted to actually cover a bunch of different tasks, and that they actually cover capture different aspects, but we really didn't study why they fail. If they actually, if one of these models they don't do a good job, what's happening underneath. We didn't actually really get time to do this, but there's absolutely some answer to this for every specific model. There might be the way that they are solving the problem might be something that is off about solving this specific task. So I think it is something that we didn't do in this paper. In this paper, it was a bit more about like proposing the benchmark, having these baselines implemented, and comparing them in high level, abstract level, not really in low level, and understand what's going on with every single model.
And maybe related to what you just said, what is the long-term plan also for ELRA? Will you add results from other transformers in this survey, other models?
We actually, interestingly, we decided to keep the archive paper alive. So every 6 months, we just add an appendix with the latest result that we have. So people keep sending us code or new results, and we try to somehow like verify and run the code, or somehow find out that how they model perform. And then every time that we have something confirmed, we just add it to a table in the appendix. And then if you actually check, so the paper is on open review, it's kind of like fixed, but the one in the archive, we're keeping it updated, so that there are, I think we have planned to do that every 6 months in terms of paper. And also the GitHub page, we also want to keep that also like, it's not like a really professional leaderboard, but we want to keep that also updated with the new ideas that are coming. This is one thing. Another follow-up is also we want to really find out how these transformers are compared in terms of decoding, and if we have a task that also involves decoding, like language modeling simply, right? Something like Lambda that really requires, it's a language modeling task, but requires capturing long range dependencies. That's also really interesting, but probably some of these models like Leanformer, because it does this low rank projection of the input, you somehow lose the meaning of the sequence and position at some point, and then this is not really possible to do that. But that's also one of the future direction for LRA to also explore tasks that they also involve language modeling or decoding.
Great. And maybe we have time for one more. The last question that was asked here is, how do you compare these two perceiver, DeepMind work, and bottleneck-based approaches similar to that? While perceiver only does classification, don't you think that learning compact embeddings would be the way to go forward for longer sequences?
This is, I think that's a, basically it's a valid comment that, as I said, like different, for example, if you think about star transformer, that's also something that introduces or solves the problem, but in a way, it also has this like unavoidable pooling mechanism that every time that you want to process a long sequence, you need to pool it, and then the output of this attention, or after this like attention mechanism that is efficient on long sequence, you have a new sequence. And then, for example, if you want to do that, it's not just about the embedding of the sequence or something, but also sometimes you really need something like machine translation, for example, like assume that you want to do long document translation, right? And then maybe you need like an encoder that gives you embedding per token, even not embedding per like the whole input, because most of the time the cross attention in machine translation is one of the key components that gives you the boost in the score. So I think it would be really nice to see something that doesn't really change the way transformer works, but just makes it efficient instead of introducing some constraint like pooling or making it possible only to do classification, or maybe compressing the whole things even in one embedding, one like single embedding. That's absolutely is a bit constraining. But in general, it's a valid point that we are looking forward. I think to some extent, some of these are doing this job, but they're not perfect. But I think it's interesting to see those that they don't pose any extra constraint on the setup that we have currently, and those new models that are efficient, but also applicable to any task that transformers are applicable. So that would be a really great direction if people start working on.
Fantastic. Thank you so much, Mostafa. Great to hear about your work. And yeah, highly recommended to check out the repo if you haven't already. Thank you so much again. And I think we're perfectly on time for the last talk of today, which is by Rohan. Rohan, are you there?
Yes, I'm here. Hi.
Perfect. Hi, welcome. Rohan Anil is also at Google, and he'll be talking about scalable second order optimization for deep learning. Very excited to hear your talk.
Thank you. So yeah, if one of you could give me a 10-minute warning for 30 minutes.
Oh yeah, sure.
Yeah. Okay, cool. So yeah, I'm Rohan Anil. I'm going to talk about scalable second-order optimization for deep learning. Has joined work with Vineet Gupta, Tom Koran, Kevin Regan, and Yoram Singer. We have the distributed JAX implementation link here. So my research focuses on making neural network training efficient at scale. And this work is about making shampoo, a second-order method, work well in practice. There are several other things that you can do to make training efficient at scale. So some of them are listed in these slides. So why? So largely we've been making small improvements to first order methods, and they've reached a plateau, both in terms of convergence and its implementation performance. And second order methods give the promise that you can get to the solution faster and possibly efficiently. So before we start the talk, why is it called shampoo? Because it has to do with preconditioning. And this is credit to Roy Frostig, who came up with the name of the optimizer. So I'll just introduce a general notion of preconditioning and intuitively explain why this might work. So we have a function f that you're trying to minimize, and we have weight vectors w and rd. For every time step, you get the gradient gt, and then you pre-multiply the gradient by the matrix ht. ht is what we mean by preconditioning. So you're preconditioning gradients with this matrix ht. If you get the second order gradient or the Hessian, you get the Newton method. And if you have exponential family, you get the Fisher or natural gradient. And the focus of this talk would be making efficient version of full matrix Adagrad. On the right, it's a very simple problem of two parameters, quadratic, and it's an ellipse that's rotated and scaled in one of the dimensions. So if you take gradient descent towards the minima, you would see that it actually bounces off the level curves of this function and zigzags to the solution. If you had a good HT matrix, you could actually pre-multiply it with the gradient so that like your loss surface looks spherical. So geometrically, you can think of the preconditioner as a way to scale and rotate your gradients, whereas the first order methods only scale the gradients. So what is full matrix Adagrad preconditioner? It's derived from the online setting. Essential idea or operation that you have to do is take your gradient vector, take the outer products of gradient vector, and take the inverse square root. And this was actually jointly proposed in two papers in 2010 from Google. However, if you try to apply full matrix Adagrad to say a fully connected layer of 3.5K by 2K, you would see that you would very soon run out of memory because you would need about 53 trillion weights to actually keep this preconditioner. So what we typically do geometrically, you can think of as take the diagonal elements of this preconditioner, and that's what we use, and that's diagonal Adagrad, and that's what's used in practice. And now you can add variations on top where you do not sum across all time steps. You do exponential moving average, in which case you get RMS prop, or you can add momentum, then you get Adam. Clearly, the full matrix Adagrad is quadratic in memory in the total number of parameters and cubic in the total number of in computational cost. Whereas diagonal methods, or first order methods as we call it, is quite cheap. It's linear in memory and linear in computation. So the question we have is, can we bring back some of these correlations between gradients of parameters, as well as maybe in regimes where you are even memory constrained, can we build a better method that keeps less memory than diagonal Adagrad? The answer is yes. So the talk today will be about shampoo, which is basically combining ideas from these three papers. And we have another work on SM3, which also has a JAX implementation, and it allows you to reduce your memory cost to sublinear space. So as you see here, shampoo actually reduces the memory cost to quadratic in the dimension of the tensors and cubic in the dimension. So it's almost starting to look practical. So at a high level, if you want to think about shampoo, you think of it as first treat each of the layers in a neural network independently. So that's the block diagonal approximation, and come up with a Kronecker product approximation to the full matrix Adagrad statistic, which I'll explain in the next few set of slides. So the next three set of slides is mainly the crux of shampoo. And once you get it, it's quite easy to get through the rest of the slides. So we have a fully connected layer. On the right, you have a dense network. Let's look at the weight matrix for the first layer, which is a tensor of size 4 by 5. And you would get a gradient also of JAX dot gradient. You would get a gradient of size 4 by 5. And let's just go with it and just compute these two statistics, LT and RT. LT, let's call it the left statistics, and RT, let's call it the right statistics. And they're formed by just doing matrix multiply between the gradient matrix and its transpose, and the other one gradient transpose and the gradient itself. And then you can sum across all time steps. So if you wanted to do full matrix Adagrad, as I showed pictorially before, you could take the gradient vector, which would be a 20 dimensional vector, and you can take the outer product and accumulate. And of course, this would take a 20 by 20 matrix. And when you have large number of dimension, when your layers are very large, you would have you need to keep a lot of memory. So the shampoo algorithm essentially proves this loner order, which you can basically to prove that it converges. is an approximation to full matrix diagram by creating these canonical product of these LT and RT matrices. So sketch of the shampoo algorithm, it's quite simple. So on the left, you add these statistics up over all time steps. So you just compute the L plus G matrix multiplied by its transpose, similarly asymmetrically for the right statistics as well. And when you want to make an update, you actually only have to pre-multiply the gradient with the left preconditioner. Here, the preconditioner is the inverse pth root of the left statistics. And on the right, you have the inverse pth root of the right statistic. Clearly, this could be expensive, and this is one of the challenges in actually making any type of second order methods work. You would have to deal with matrix inverses, usually. So the other challenge that we have when applying shampoo to increasing into transformers is this increasing model size. As you all know, like the model sizes have gotten very large. Now, when I started working on optimization, it was 300 million parameters, but now it's normal to have 100 billion parameter models. So typically model sizes are increased by increasing the number of layers, in which case the shampoo memory only increases linearly. But if you increase the layer width, of course, the shampoo breaks down because now you have to keep quadratic in the dimension of the tensor, and that's not going to work. So what we do is very simple. So for example, this is a very large tensor, which is typical of transformer models. We have an embedding layer of size 32768 by 1024. We find that actually on the left, you have a picture of a transformer. You actually improve convergence by just keeping one of the preconditioners, the right preconditioner. And for models like PCTR prediction with the Criteo DLRM model, where you have number of vocabulary items to be 186 million, you can even efficiently compute this by just taking the outer product of the gradients of the input layer. And we also see that it improves convergence there. So if you have a very large dense layer, it's also a block diagonal approximation. You can split those up into smaller pieces of 1024 by 1024 and run shampoo on each of those, and we still see improvement. And we'll show you results later on ResNet 50, where we are able to train quite fast by splitting it up into tensors of size 128 by 128. In actual practice, we also reshape the gradients to increase the amount of correlations. For example, if you have a gradient tensor of size 133, 1024, 1024, we would reshape it to 9, 1024 by 1024. And typically, the tensor and shampoo is constructed based on the dimension of the tensors. The tensor dimension might be different based on the implementation choices. So how do you compute these inverse pth root? It's very simple. We just apply the Newton method you can run this on a GPU or a TPU. The Newton method is the following: x to the power p times a. We are trying to compute the inverse pth root of a should be equal to the identity matrix. And that's the update equation that you would get when you straightforward apply the Newton-Raphson method for matrices. However, that update is that iteration is actually unstable and makes certain assumptions on the eigenvalues of a. So we make a simple modification. The modification is to rewrite x to the power p times a as m, and then you get to something called as the coupled iteration. And you can see the JAX code for it, and this allows you to do very fast inverses, very fast inverse square roots, and very fast inverse fourth roots. And you can find a lot more efficient methods in this book. The other problem that we have to deal with is the statistics matrices might be very poorly conditioned. So this is the Overton rule of thumb for matrix functions. So a function like inverse pth root, you would lose these many bits of precision. So here kappa of m, the M matrix that we're trying to compute the inverse pth root, is basically the maximum eigenvalue of the matrix divided by the minimum eigenvalue. And if you have something like float 32 and you're trying to compute the inverse pth fourth root of it, you would lose about 19 bits of precision, and essentially you're left with 4 bits of precision, which means that you might not get the full benefit of preconditioning. So this is what happens in a real model. The inverse pth roots, we're looking at the maximum and minimum singular values. We see that we do see large condition numbers. So what could you do to address this? You have to run these inverse pth roots, which are expensive, but it's done for each layer. And so there's a natural parallelism. One thing you could do is to run these inverse pth roots on the CPUs that is doing your input pipeline. So what you do in JAX is to outside your device loop, you would gather your statistics and compute these inverses and push back those preconditioners back into the TPU. This works quite well, and you can implement this if you have a very large training pipeline. And we find in practice that you don't actually need to run these inverse peer-throughs very often. For transformer models, we find that a delay of 1,000 steps is more than sufficient to get most of the benefits from preconditioning. The other thing you could do if you don't have high precision numerics is to actually emulate them using smaller precision. So for example, this paper from Intel shows how you can leverage bfloat 16 units to actually emulate floating point 32 units. So it's using fewer more matrix multiply, but this means that you don't actually have to have these big area on the chip to do this matrix multiplication. So this allows us to actually move the inverse peer-through to the accelerator that's running the computation, and the choice of where you would put it is based on what type of model you're training and many of the properties of the model. For example, if you have a very large batch training, you would need to compute the preconditioners very often. And if you have very small batches, you can usually have a staleness tolerance of 1,000 steps, as I said before. And there are many other trade-offs. So JAX, for example, gives you very easy way to have select the precision you want. So for example, I'm just doing a matrix multiply, and this is part of the inverse peer-through. You have to do matrix multiply by itself, and you can actually configure it by passing a precision flag. And depending on the hardware that you run on a GPU or a TPU, you would get the right amount of precision. And this allows us to actually implement shampoo on JAX, natively running the inverse peer-through on the TPU itself. The second problem with second order methods is that you actually have a very expensive computation that you have to run. And you have to run that if it's in a data parallel regime, you have to run that in every core. Typically, first order method implementation ignores this because it's quite cheap. It's just element-wise operation. So you just run them independently once you sum the gradients on every core. So JAX provides quite powerful primitives like pmap and vmap that allows you to parallelize your expensive operation across cores. You probably already used this. So for example, you can compute the inverse peer-through across all the statistics, across all the devices in a single host or a multi-host setting. And here is some sort of actual code that I copied from the shampoo implementation that allows you to do this. So what happens when you put all of these together for a real model where there is like a benchmark that's competed on by several hardware companies? So we actually get to be the fastest in training, for example, this ResNet 50 at very large batch sizes. Like, for example, this is 3268, and it uses the same benchmarking hardware, and it actually beats first order methods and gets about 31% reduction in training time. Now, we use block preconditioning, as I described earlier. This allows us to run these inverses every step, and it's quite fast. So we actually use this, and recently we submitted this to the MLPerf 1.0 open submission, and you can find even faster results there. So we recently used this to actually improve a real use case where you actually wanted to train a ResNet 50 to the highest possible accuracy. So in this paper, we actually use shampoo to get about a 4x reduction in training time to get ResNet 50 to the same accuracy. So this ResNet 50 gets to about 82.8% accuracy, and you can read about it in this paper. And clearly, a lot of people are probably interested in transformers. These are some of our results where we were running these inverse peer-throughs every 1,000 steps. We actually pretty much do better than Adam, a well-tuned Adam in a couple of data sets, and also across domains. For example, for PCTR prediction task, the improvement that we see here is quite large. So as I said, you have the gradient tensor, and you pre-multiply it by a preconditioner on the left and a post-conditioner or a right preconditioner on the right. So this is like snapshot of a preconditioner from a transformer training for a language translation task. We find that there's actually patterns that show up. For example, this on the right, there are these block diagonal things that could possibly be from the multi-head attention. On the left, you have these 4 blocks with these non-diagonal patterns, which probably are from modeling maybe sequences that are the tokens that are closer together. We actually noticed that when you apply these matrix multiplies, you change the signs. You're literally rotating the gradient significantly, and that allows you to get faster convergence. So the other work is SM3, which is a sublinear memory optimizer. This allows you to actually, if you have a regime where you're training with large number of parameters and you don't have enough memory to keep optimizer state like the second moments in Adam, you could use SM3, which is a version of count min sketch, to compress it into sublinear space. So think of this as the diagonal entries of the shampoo matrices that I showed you. So, I'm ahead in time. So so this is the talk. SM3 is already available in Optac, so you can use it. Shampoo is already available in the pre-linen version of Flax, and the Optac version will be out this week. If you have any questions, let me know. And we can use the next 10 minutes to maybe ask me questions and I can answer them.
Awesome. Thank you so much. Super impressive results. We did have a few questions that you maybe partially addressed already. So the comparison between SM3 and shampoo, you mentioned briefly.
Yeah, so SM3, you can think of it as it pretty much matches Adam, and shampoo does better than Adam in majority of the cases.
And let's see, you also said it is available. Somebody asked if it is available kind of as a straight out of the box usage.
Yeah, you can, if you use Flax, you can call the distributed shampoo from our code base. It's open source. I have the link in the first slide. You can just use that to train your models.
Awesome. And how's the performance of shampoo in GPU versus TPU?
So it's about, I haven't done very large amount of benchmarks because I mostly use TPUs. So it depends on a lot of things like how fast, like for example, TPUs have very efficient communication. So these PMAPs run blazingly fast. On GPUs, you need to have NVLink and other things to get those communication to be fast. So it sort of depends on the hardware you have. So it's a very nuanced question to answer. So it depends on the versions of each of these devices.
Somebody asked about hyperparameters. How well do those values transfer for a task to another task?
Great question. The hope was that second order methods would allow you to do fewer hyperparameters, but that's not true. It's the same amount of hyperparameter tuning as first order methods. The default one generally does well, but once you tune those hyperparameters equally well as first order methods, you get better results.
Cool. And let's see. Are there some use cases where we should use SM3 versus shampoo?
Right. So it depends on the model. So like open question that we haven't answered is that, do you need to train a very large model, or do you need to train a smaller model with a better optimizer? So what is the efficiency gains from a better optimizer in decreasing your log perplexity or whatever metrics you're looking for? It's not clear to me right now. So for example, if you can increase the number of parameters to the point where you don't have enough memory to store atoms, so in which case you could use SM3. So that's a quite open question. One thing I could say is the smaller the model, the more hyperparameter tuning you could do. So you could probably see benefits. So for example, in the one place where we actually have data is this PCTR prediction task. So the improvement that we get here is more than what you get by making the embedding sizes 8x larger. So if you make the models 8x larger, you get about 0.25 or something, and we get way more than that by just using a better optimizer. So ideally, if you have the hardware, you should do both.
Is shampoo less sensitive to how you set the overall learning rate?
So it's very, again, it's sort of like for the InterASNet experiments, all the hyperparameters for different batch sizes are checked in. It actually, like what we find is that when you tune, there's no like linear scaling law or something that you typically prescribe. The batch size is 32768, uses a learning rate of 16 because of related to how the gradients are summed, and the batch size of 65K uses a learning rate of 12. So unclear to me how to actually answer this. We've been answering it by hyperparameter tuning, so giving equal amount of tuning to baseline and the optimizer to see which one works better.
Makes sense. We have a question on your background. Someone is really interested in your research background, and how did you converge toward your current line of research?
I've been at Google Research for the last 6 years now. I've been working on applied machine learning for those amount of time, and I been working on, I guess, applied ML at Google on internal products. And I guess in the last 3 years, I've been, and even during those times, I was mostly working on efficiency, different types. So before doing research, I was actually programming, I guess, a systems programmer, working on optimizing actual servers and things like that. In terms of research career, I guess the efficiency makes me like motivated because it's real. And yeah, so hope that answers the question.
Yeah, cool. There's one more question coming in on these plots. It looks like models didn't converge yet. Do you expect final performance would be different, better for shampoo versus Adam?
Yeah, so typically, so for transformer models, these improvements are consistently like this across time steps. One could do learning rate decay at the very end to get some performance out of averaging, and that is like on par for both cases. So it's yeah, so it's typically you would see the same type of results. In large scale, what I've seen is shampoo gets to better quality, but it might be just trainability. If you show more data to the first order methods, it probably reaches the same accuracy. For example, it's kind of verified in the ResNet 50 experiments here. So like Adam is the blue line. It also reaches the same accuracy given enough time.